that same base that we kept looking at yesterday, but we have triangles or semicircles. This won't do semicircles. It does a full circle, but most of the questions that we get usually end up being semicircles. But you can get an idea just by looking sort of like at the top part. If I go across, you can sort of see that you have these teeny tiny semicircles on the end. The biggest ones in the middle, if we do the trace the slices so that it will show us. It wasn't blue yesterday, was it? I like blue better than the color we had yesterday. So you can kind of look and see what you would end up with here. It would give you this shape. This is a full circle, so it's on both sides, but if it was a semicircle, it'd only be the top half of that there. If we reset it, you could also do an equilateral triangle. An equilateral triangle would look like this. I think we looked at this yesterday. It keeps changing colors. We'd have this, like all those triangles there. We also could have another type of triangle. Let me reset it again. We could have a right triangle where the leg is in the base, so you're looking at like a right triangle that looks like this. And if we look at this one, it makes a pretty cool looking shape here. It's sort of similar to what we just did with the equilateral, but it's all slanty right here, where the equilateral was, you know, straight there. So it'll make all these cool shapes here. So the main difference of what we'll be working with is that formula for our area. Yesterday, our formula for our area was either the side squared, because we were doing a square, or it was a rectangle, so it might be length times width, or something like that for those. So let's do a problem. A solid has a base that is bounded by the curves y equals x squared and y equals 2 minus x squared in the xy plane. Cross sections through the solid perpendicular to the base are parallel to the y-axis, and they're semicircular disc. Find the volume of the solid. Okay, so we've got lots of information here. One thing real quick, is this going to be in terms of x or in terms of y?
Y.
Are you sure?
No, yeah, Y. No, Y.
It feels like it should be y.
No, it's X.
Okay, why is it x instead of y though? Because it says y-axis right there.
It'd be Y if it was perpendicular.
It says parallel to the y-axis, right? So a cross-section parallel to the y-axis would be perpendicular to the x-axis. So this problem is going to be done in terms of x. That's tricky and kind of mean whenever they do that. But watch out for it. If it says parallel to the y-axis, it's actually an x problem, because you're looking for what it's perpendicular to. All right, so we need to kind of sketch a graph of what we've got here. This is just y equals x squared, and this is y equals 2 minus x squared. So this is just a regular parabola that has not been moved. This one is a parabola that's upside down and has been moved up 2 here. It might be helpful to us to see where they cross first. So that helps you do your graph a little bit better. So if I have x squared equals 2 minus x squared, I could add this x squared over here to this side. That's going to give me 2x squared equals 2. Divide by 2. X squared would equal 1. So x is going to equal plus or minus 1. So my intersection points are at positive 1 and negative 1. And if I sketch a graph of what I'm looking at here, actually, my y-axis could be down lower. Hello? Yes. Thanks. Bye. Lily and Reagan, they need you guys in guidance with your computers. All right, so I'm going to mark, this is 1, this is -1. That's where we should intersect. I know I need to go up to 2 right here. So y equals x squared will look like this. And then if we graph y equals 2 minus x squared, that is going to have y-intercept at 2, and it's going to be upside down. It will look like this. It is close, but on the website, you've got a 4 right here. So like, if I can change it, this one will graph for us on this website. We can make that x squared, and we can make this one 2 minus x squared. So it's a little bit smaller than what we're looking at there. And if I change my bounds from 1 to -1 this time, we can actually get a picture of what this is going to look like. And, well, we can almost get a picture of what this is going to look like. We want circles, or semicircles. The website only does, oh gosh, I can't get it to turn like I want it. There we go. The website only does a full circle instead of semicircles. But if we imagine it's just like the top half, gosh, that's not a very good picture of it. Let's try again here. I think I do. Alright, it's just hard to, it's just blue. Alright, come on. Oh, there it went. It's kind of hard to see, isn't it? It's not doing great. There we go. We're looking at something like this. It'll be only the top half, though. It won't be the bottom half because we're only doing semicircles there. But we got all these little tiny circles right here. So, our cross sections are parallel to the y-axis, which means they would be going this way. Okay, so we would be taking cross sections here, and for each little one, we'd be like, over here, we'd build a tiny little semicircle. And then over here, we'd build a bigger semicircle. And if I try to start drawing them all, it'll be hard to see, but they'll get bigger as they go towards the middle, and then they'll get smaller as they go towards the edge over here. So, if our cross section is a semicircle, we're working with the equation for the area of a semicircle. What is the equation for the area of a semicircle? Alright, very good. We are doing pi times radius squared times 1/2, right? So it is half of our area for our circle. Okay? That would be your area for your semicircle. Now, we need to find the radius, right? So radius right here is this length. Now, notice that does not go all the way across because radius is just from the center of that circle there. Now, what we've been doing for these others, we've been doing like top minus bottom, but does this bottom number hit on a line? It looks like it's at 1, but you don't want to make that assumption. I think it is correct in this case, but I would not make that assumption. It would be a little easier here if we found the diameter first, right? Because the diameter would go all the way across that circle, right? So I'm going to call this D right here. So if our diameter we're looking for here, it would be the top function minus the bottom function. So the top function is the green function, which is 2 minus x squared. And then the blue function is the bottom function here, which is x squared. And if I want to simplify that a little bit, it is just going to be 2 minus 2 x squared. Now, that is my diameter. That is not my radius. What do I have to do to that to get the radius? I got to divide it by 2. So my radius is going to be 2 minus 2x squared divided by 2, which we can do the love connection on here. We'll just get 1 minus x squared. That's my radius. So that radius can get plugged in up here for your r. Okay, very similar to what we were doing yesterday, but the radius is going to be half of the diameter. You'll have to find the diameter first. The diameter is just like we were doing here. We're doing, like this is y, but right minus left, or top minus bottom, but then you have to cut it in half since semicircle requires a radius. So, we are going to have the equation a of x equals 1/2 pi times 1 minus x squared squared. And then I need to integrate this. That's the area of one semicircle. I need to integrate this to find the area of all the semicircles added together. So I'm going to take that formula, 1/2 pi 1 minus x squared squared. What do my limits need to be when I integrate? -1 to 1. We're looking at the x-axis because this is in terms of x. So that's from right here at -1 to right here at +1. If it were y, what would we have to do? 0 to 2, but we're not doing it in terms of y, so we want to look at the x-axis here. Okay, I'm going to do this one by hand, but this is the only one we're going to do by hand here. So 1/2 pi is just a coefficient. I would pull it out. So I've got 1/2 pi integral from -1 to 1, and we need to square this out. So we're going to have 1 minus 2x squared plus x to the 4th. If we square, double square there. Because we can't take the integral whenever it's got that square there on the outside. So I'm right there, I'm just doing 1 minus x squared times 1 minus x squared for that. Then I need to integrate. So when I integrate, the 1/2 pi just sort of hangs out front till the very end. I will have x minus, I'm going to have 2/3 x cubed plus 1/5 x to the 5th. And we will integrate this from -1 to 1. And so, again, the 1/2 pi staying out front. We're going to have 1 minus 2/3 times 1 cubed plus 1/5 times 1 to the 5th minus -1 minus 2/3 -1 to the 3rd plus 1/5 -1 to the 5th here. So we got 1 minus 2/3 plus 1/5. Half pi stays out front. Over here, we're going to have -1. This is going to be plus 2/3 and minus 1/5. But then the negative needs to be distributed. So, now if we were on an FRQ, we could have stopped right here. Right, FRQ, we don't have to go past this. But let's finish this one out. The rest of them we're going to do with the calculator or just set up. 1 minus 2/3 plus 1/5 plus 1 minus 2/3 plus 1/5. So we're going to have 2 minus 4/3 plus 2/5 there. Lost my pi. Let's get common denominators. We're almost there. They might have you do this by hand, but I feel like this is sort of the maximum of what they would have you do by hand. So you got 10 over, no, we needed 15. So we got 30 over 15 minus 520 over 15 plus 6 over 15. I'm going to do pi over 2 there. Alright, so we got 30. That's 20, we give us 10. We got 16 over 15. That 16 can reduce with that 2, so that'll make this 8. And that'll go away, and we'll get 8 pi over 15. So that would be our volume of that figure. Like I said, this is the only one we're going to do all the way by hand that far because they can be a little bit extensive. The setup is what I'm really concerned with because a lot of times these questions don't have you actually solve them anyway, or it's calculator active for that. Okay, questions on that problem? Good gracious, look at that. Isn't that beautiful? Let's look at the whole thing all together. It's impressive. Yeah, you gotta go show your mom that one. All right. Okay, next one. Okay, these are going to be a little tough when we have equilateral triangles. They're going to be a little difficult to do because an equilateral triangle, if we start off with this, an equilateral triangle, let's make this bigger. Equilateral triangle, all the sides are the same. So like this side is S, this side is S, this side is S. But how do we find area of a triangle? You could do S times H, but you'd have to put divide by 2 with it. So if I've got an S right here, it would have to be base times height divided by 2, or we could say S times H divided by 2, or we could do 1/2 base times height, right? Now, here's the problem. Is that height equal to the S here? It is not. And my picture is, let me make my picture a little better so this makes a little more sense. Let me use the actual equilateral triangle here. Oh yeah, that's better. So this is S, this is S, this is S. This right here is our H. Now, we're not going to be able to do this with 2 different variables there, right? A square is a lot easier because it's just like S times S, right? You can use both of those. A rectangle is not that bad. If they had asked us to do a right triangle, you could, Liam, because you can make this a right triangle where you would have S times S, and then you cut it in half. But an equilateral triangle doesn't cut it in half. You'd have to slash it this way. So if it is a right triangle, which they do give us sometimes, it is much easier because it's 1/2 S squared. So that would be for a lot of times they'll call this an isosceles right triangle with a leg in the base. Yes, you can use the King's theorem here if it asks you for that. But this is not what they ask us for on this problem, so we can't use it here. So save that for later. You are going to see some problems where we do that. But this we cannot do. So we've got to get this all in terms of S. So this is a right angle right here. What's the length of this side right here? It's half of S. Right, because that, since this is equilateral, that height, that altitude should cut that bottom side in half. All right, so we've got a right triangle here. What can we do when we have a right triangle? With our sides. Something that's always true about the right. The Pythagorean theorem. So you can do a squared plus b squared equals c squared here. So that is going to be h squared plus, I'm going to call this s over 2. It just makes it a little easier to do. Squared equals s squared. Okay, and what we want to do is we want to solve this for h. Okay, so we got h squared plus, this is going to be s squared over 4, because you're going to square the top, square the bottom. That's going to equal s squared. What would I need to do next? Move all the s's to one side, so I've got h squared equals s squared minus s squared over 4. Now both of those are s squareds. I can put those together. What am I going to get? This is a 1 right here, right? This is like having a 1/4 s squared. So if I do 1 minus 1/4, I'll get 3/4 right there. So h squared equals 3/4 s squared. And then what do I need to do? I can what? Square root both sides, because I'm trying to get h by itself. So h equals square root of 3, I cannot do. What's the square root of s squared? S. What's the square root of 4? 2. Okay, we're still not done. This needs to go back up here and be plugged in for our h right here. So our area formula is going to be s times, actually I'm going to write it this way. Let's make this formula look like this. It'll be a little easier if we make it look like this. 1/2 s times h will just be a little easier to combine right here. So let's do that. We're going to have 1/2 times s times our h is the square root of 3 over 2 times s. There. And so our area is going to be, well, we can multiply the 1/2 and the square root of 3 over 2 together. We will get square root of 3 over 4. And then we got s times s, which gives us s squared. We have barely even began the problem here, because that is just our area for an equilateral triangle. We haven't even looked at our base and all that stuff yet. Now, the good news is if you have a good memory, this is always going to be the same for an equilateral triangle. This is always the area of an equilateral triangle. So, if you have a good memory, you can just memorize that and you don't have to do all that work over again. My memory's not great and it's getting worse every day, so sometimes I just have to go work it back out again or go look it up because I can't remember. But if you are really good at memorizing those things, like the work that all the work I have just done is not required to be shown on this. It's just required because Ms. Hyatt can't remember what the formula is and needs to go through it. So if you have that memorized, you can just use that. All right, but that's just our area of equilateral triangle. We're going to need it, but we got to find the s and plug that in and then integrate, right? So to know about the s, we have to graph this. Are we going to be in terms of x or in terms of y? Cross sections perpendicular to the x. They didn't try to trick us here. They said perpendicular to the x. So we're in terms of x, which is good because our equations are in terms of x. We're not going to have to do anything crazy here, like solving for y. What types of equations are those? I've got f of x equals 1 minus x over 2. And I've got g of x equals -1 plus x over 2. Yes, they're linear, right? They don't really look linear, but this could be written this way. I could write it negative 1/2 x plus 1, and I could write this one 1/2 x minus 1, and those definitely look linear, right? So linear problems are not very hard to sketch a graph for. In fact, I would rather sketch a graph than try to do this one with the, like by setting them equal here. The graph will be a little bit easier. So if I graph this, let's see, what we need, 1, 2. All right, so let's do this first one. We'll do this first one blue. I've got a y-intercept at 1 and a slope of negative 1/2, so I go down 1 to the right 2, and that is going to give me the blue line that I have here. Let me change my axes to black so it shows up a little better. Okay, and then if I graph this one in green, g of x is green, I've got a y-intercept at negative 1, a slope of positive 1/2. That's going to be here. And I've got this. So the base for this problem is this area in between right here. And so I'm perpendicular to the x-axis for my cross sections. So I will be taking a slice like this. That would be like my S, and then from there I'm building the equilateral triangle off of that slice, right? So S for this is going to equal top minus bottom, which equation is my top, f of x, so negative 1/2 x plus 1 minus the bottom, which is my green, so that is 1/2 x minus 1. And so if I distribute that negative there, I will get negative 1/2 x plus 1 minus 1/2 x plus 1. And so negative 1/2 and negative 1/2 is just going to give me negative x. 1 plus 1 will give me 2 there. So that is my S. S needs to get plugged into my area formula here. So I'm going to take this, and it gets plugged into my area formula over here. Okay. So my area formula is going to be a of x equals square root of 3 over 4, and then I will have negative x plus 2 squared. I'm going to stop for a second here and see how we're doing. Yeah, you could just pick, like, you could set them equal to see where they cross to know what your limits need to be, and you could like plug in to see which one's higher, or you could just be able to picture it in your head there. So you don't have to draw the graph. The graph helps me a lot on these, especially if it's one I know how to graph, like this one. All right, so we're almost there. Once you get to this point, you've came a long ways. Now you just need to integrate, because this is the area of a single triangle. To add them all together, you just have to integrate. We are going to now integrate. What are our limits of integration? Zero to 2, not negative 1 to 1. That's what we use if we were in terms of y. And so we'll have square root of 3 over 4, negative x plus 2 squared dx. Okay, and I am not, Not really any worse than the last one to do by hand, but we don't have time to do all of this by hand. It's unreasonable to assume that we would do that. So let's okay. Alrighty. Let's use our calculator to type this in. So you can use Y1 if you want, or you can just type it in. I think I'll just type it in on this one. Gotcha. So we are going to integrate, and we need square root of 3 over 4 times negative x plus 2 squared. We're going to put comma x, comma 0, comma 2. And I'm going to hit the green button before I hit enter. 1.1547. I almost feel a little sad that we didn't work that one out by hand, because if you just want to sit back and admire your work, think of how much more work we would have had there and how much more impressive our problem would have looked. Still pretty impressive even as it is right here, but not impressed. Yeah. Yeah. That's what you're going for when you show your parents. Unless your parents are really, rarely do I ever have parents. I have lots of parents that have had calculus before, but they usually cannot still do calculus.
See, if I sent a picture of this to Jack, he'd send me a picture of him doing his work, and like,
yeah, he would just like show you up. Yeah, yeah. We like when I used to work at the day camp. Some of the guys like were basketball players or had been in high school, and they'd be like dunking on like 10-year-old kids during rec time, and that's sort of the same. So, all right. Okay, I think we're getting it close. Okay, we need to do one of these, so we're going to do this one, or at least get it set up. We might not even type this on the calculator. Base is bounded by the circle x squared plus y squared equals 4, with cross sections that are isosceles triangles with the hypotenuse as the base of the solid. The cross sections are perpendicular to the x-axis. I've done x-axis on everything here. I might not should have done that. Should I switch this one to y? Let's do a y. What's the next one? What's the cross section on the next one? There's a semicircle, so I'll do that one. Because we definitely don't have time for both of them. We got to do FRQ. Let's just change this one to y. We can do that. Because it will be, I think you get the same answer actually. Because the circle really isn't going to matter. But let's do it in terms of y just so we're. Now, this one's a little bit funny because it gives you the equation of the circle, and it's not in terms of x or y, right? It's x squared plus y squared equals 4. It's what we call an implicitly defined function because it is not solved for either variable. If we want to do this with cross sections perpendicular to the y-axis, we want to solve that equation for x. So we are going to say x squared plus y squared equals 4. We will need to subtract our y squared. And so x squared will equal 4 minus y squared. And we will have to square root both sides. So we will get x equals plus or minus the square root of 4 minus y squared. Now, that's really two separate equations, and we'll talk about that in a second when we graph it. Okay? So, if I graph this, it's just a circle. Where's the center of the circle? 0, 0. What's the radius of the circle? 2. Because your circle equation is x squared plus y squared equals the radius squared, right? So, if we graph a circle that meets these requirements, we're looking at this. let's fix my tick marks there so this will look. We'll move that tick mark in. It's not in a good spot. All right, now, to do this problem, I can't have x squared plus y squared equals 4 as my equation. I have to use this. And so, what we're seeing here is this half of the graph, the right side of this graph, that is going to be x equals positive square root of 4 minus y squared. It's a semicircle. It's the positive half. It's where, because if you plug in numbers here, you're going to get a positive x coordinate, so it's the right side. If we did it in terms of y, the positive would be the top half, and the negative would be the bottom half. I'm sorry, if we did it in terms of x, this is in terms of y. And then this half right here is the equation x equals negative square root of 4 minus y squared. There. And we're going to be doing cross sections that are perpendicular to the y-axis. So, like if I let this side right here be s, what would the value of, how would we find s? What would it be? Whenever, well, you're thinking of the equation of the triangle, and we are going to do that in a second. But right now, just for s, like just for that value s, the length of s is going to be whatever the blue graph is minus the green graph right here. So it would be square root of 4 minus y squared minus negative the square root of 4 minus y squared. All right, so the right side is 4 minus square root of 4 minus y squared. The left side is negative square root of 4 minus y squared, and we're subtracting those. That's going to become, like the double negative becomes just like a plus. What is the square root of 4 minus y to the second plus the square root of 4 minus y to the second? Yes. So it'll be easier if we just do this. That is our s value. Okay? Now, what we're doing for this problem is what Liam was saying earlier, so we can use the King's theorem on this one that he named here. We're making isosceles, means the two legs are the same size. Oh, change that to hypotenuse. That's too hard with the hypotenuse. Change that to leg. That's what you usually see on the problem anyway. Isosceles triangles with the leg as the base of the solid, which means this is S, and if this is isosceles, this is also S right here. So when we're looking for the area of that triangle, what is the area of that triangle in terms of S? What's the base of that triangle? What's the height of that triangle? S. So it's going to be 1/2 S times S, which is going to be better written as 1/2 S squared. These are easier than those equilateral triangles, right? Because the base and the height, they're going to be the same. In fact, because of that, they give you these types of problems more often. All right, so what we need is S to be plugged in for our S over here, and then we are going to have our A of Y. We want to use a Y because it's in terms of Y. We're going to have 1/2 times 2 square root of 4 minus Y squared. Now let's simplify this a little bit. It'll make it a little bit easier to plug in. Whenever we square this, we have to square both things that are in here. What happens when we square that 2? We'll get a 4. So we got 1/2 times 4. What happens when we square the square root? We goes away. So we just got 4 minus y squared. So if you had to do this one by hand, it actually ends up not being that bad because it's just 2 times 4 minus y squared, which if you want to write is 8 minus 2y squared. That is our A of y formula. And so we need to, this is our area formula for this case. We need to integrate. What are our limits we're going to use to integrate? Negative 2 to 2. This is a forgiving problem because even if you forgot and looked at the x-axis, you'd still get it right. But we're looking at the y-axis, negative 2 to 2. So to set this up, and that's all we'll do for this one, would be negative 2 to 2 of 8 minus 2y squared dy. Not that hard to figure out by hand or on the calculator, but we'll just stop with the setup. Okay, so just to recap, this is the formula you want to use for a right triangle with the leg in the base, right? Over here, this is the formula for an equilateral triangle. Over here, this is your formula for your semicircle, right? So those are probably the 3 you're going to see. I don't think I gave you another one on that homework. Hope, anyway. So your assignment is going to be to those other 4 from the worksheet. Okay. Questions? All right, let's do a free response question. Which one do you guys want to do? There's 3. We've had it for a while, but I realize that some of you guys work best under pressure. So, really, I would probably not do 1. I think it's the easiest of them. I would pick 2 or 3. I think 1 is easier than the others. Which one do you guys want? Okay, everybody go look at it. Everybody find it. Dig it out of the bottom of your book bag where it's crumpled and wrinkled yet still blank.
Can't find it.
All right. Okay, for those of you who have located it, raise your hand if you would like to do number 2. If you want to do number 2? 2 and 3, yeah. I think 1's easier. They have a couple different things that can make them a little bit tricky. All right, 3. I've got some votes for 3, so we're going to do 3. Okay. Let me just remind you real quick of one thing on this one, though. If you take the derivative of h, like B is going to ask you to find h prime of 2. If you take the derivative of h, let's do this one little thing. What's the derivative of h going to be? X over 2 plus 3 times 1/2. You got to take the derivative of that limit right there, because you're doing the derivative of an integral, which kind of cancels out, but because this is not just the x, you've got to plug it in and multiply by the derivative of it. Up here, when you find h prime of 4, h prime is just f. Right, just f there. So it's a little bit easier than All right, so this one says let f be a function defined on the closed interval from -3 to 4 with f of 0 equaling 3. The graph of f prime, the derivative of f, consists of one line segment and a semicircle as shown above. All right, so this is very important. This is f prime. It is not f. It is f prime. So when it says in part A, on what intervals, if any, is f increasing, this is not the graph of f. It is not going to be -2 to, it's not going to be 0 to 2. Because f prime is increasing there, but it's asking you about f. Okay? So, how can we tell where f would be increasing? Because we don't have its graph. Where what is positive? Where f prime is positive, where does that happen? -3 to -2. So you would say f is increasing for -3 to -2 because f prime is positive on this interval. That's one of those things, I think technically it's supposed to be brackets, but if you use parentheses, they won't count off for it. Because there is some debate amongst textbooks which one's correct. I would not do that. They might take it, I'm not sure, but I would pretty much never do that. I'd either write it like this, or it'd be perfectly okay to do -3 less than or equal to x less than or equal to -2. You could do one of those two, but I would not say -3 to -2, just because it's not mathematical notation, and I'm afraid of how they might interpret it there. It also doesn't tell you whether the endpoints are included. Again, it doesn't matter on this one, but I wouldn't do that really ever on the test. All right, we good here? All right. Find the x-coordinate of each point of inflection of the graph of f on the open interval from -3 to 4. I like this problem because it goes way back. Points of inflection are where we change what? Concavity. Concavity is second derivative, right? So if you think about that chart we've used many times, we're looking for f to go from concave up to concave down, but the second derivative would change from positive to negative, but do we have the second derivative? We do not, so we cannot talk about, you can talk about the second derivative, but you can't only talk about the second derivative. The only thing we have is f prime, so we've got to talk about f prime to explain this. If f double prime is positive, what's that tell you about f prime here in the middle? Increasing, and this would be decreasing. So if we switch from increasing to decreasing on our first derivative, or vice versa, we're going to have a point of inflection, right? Where does that happen? 0 and 2. All right, so you would say f has a point of inflection at x equals 0 and x equals 2 because f prime switches from increasing to decreasing or vice versa at these points. I would not suggest abbreviating like I'm doing on the real thing, but I don't have a lot of space right here because I didn't format these very well. Alright. Are we okay so far? This is all so far just like earlier stuff, right? C is still earlier stuff. It's a tangent line. We were really good at tangent lines at one point. What do you need for tangent lines? Point, a slope, and the equation of the line, right? So it gives us the point. We don't even have to find it. How do we find the slope? Is there a 0, 3 on this graph? No, because 0, 3 is on F, but we know the x coordinate is going to be the same, right? So we're going to look at where x equals 0, and we're going to find f prime of 0, right? And so it's negative 2. You need to write that down. Don't just go straight to the equation. You're going to write down f prime of 0 equals negative 2. I know you're just pulling it from the graph, but you need to write this down because sometimes there's a point there, just for finding the slope of this tangent line. And then if we write our equation of the tangent line, it's going to be negative 2, parentheses, x minus 0 plus 3. Of course, it's fine to leave off that 0 if you want. I don't know. That's one of those things I'm really eager to learn whenever I grade this time, because I'm not sure. I think it depends on how the points are separated out. But if they put a point for finding the slope and you don't show where it came from, I'm not sure if you're going to get the point or not. So I would just write it to be safe. Okay? All right, so last part, and this is the current part. This is the stuff that comes from Unit 8. We need to find f of negative 3 and f of 4. We don't have the graphs for f of negative, or for f, right? But we do know that f of 0 equals 3. That's going to be our starting point, right? I'm going to actually find f of 4 first, because it's going in the positive direction from f of 0. So if I want to find f of 4, what I'm going to have to do is I'm going to have to take whatever f of 0 was, and I'm going to have to add how much the function changed between 0 and 4, which is going to be the integral from 0 to 4 of f prime of, this is x or t? Does it even say? It's x. F prime of x dx. Now, they tell us f of 0 equals 3, so we're just plugging in a 3 right there for that. How do I find the integral from 0 to 4 of f prime of x dx? What? Is not f prime 4. We're not taking the derivative of it. What? It is f of 4 minus f of 0. That is correct, but do we know f? We do not know f, so it's not helpful here. It could be if we knew f, but we don't know f. So that is correct, but not helpful here. It's area under the curve. If we have a graph, our integral is our area under the curve. So we're talking about the area between this curve and the x-axis. So we're looking at, let me get the highlighter here. We're looking at these little pieces right here. Oh, just switch colors right there in the middle. That for me. Keep things interesting. All right, so how am I going to find that? Area of the rectangle minus area of that semicircle, right? So the rectangle would be just 4 times 2. And then we will subtract the area of the semicircle, which is going to be 1/2 pi times the radius squared. What's the radius of that circle? 2 squared, like that. You can leave it like that for the sake of time. I am going to leave it like that because we got to go. All right, we got to do f of negative 3. We still have to start from f of 0. We're going to have to integrate from 0 to negative 3. What's wrong with that? My limits are backwards. The highest one is the lower number, right? So I could rewrite that as, this is going to be a 3. I could write it as minus the integral from negative 3 to 0. F prime of x dx. And then that is the area under the curve from negative 3 to 2. So we are looking at this area here and this area here. So 1/2 is the area of this part right here. And it is positive. That's the part above. And then we're going to have a minus because this part is underneath the curve. And that's going to be 1/2 times 2 times 2. So 1/2 times 2 times 2. Like that. You can leave it. That gives you a whole number. I wouldn't leave it probably if it wasn't for the fact that it's already 949. So I'm going to stop right here. What you could do.